All right, class, let's continue. We're in 2.5, is that right? Measures of position, where you're at there, and not going to go over it. We are halfway through this chapter, so we're going to just jam through a few things here. Quick reminder, I know it's been 2 days, so let's go for it here, and then we'll jump to it. I skipped around a little bit towards the end of class, so I'm going to kind of go in order, and let's kind of fill in the order, because it should fill in nicely here. I'll show you a couple of things. All right, so how do we do this here? Bless you. And Quincy, I'm going to go kind of fast in the beginning, and then we'll kind of slow down as we get through. Okay, so how do we do this? We break it up into, we call them fractals, which is you're just dividing things, or partitions. We can do it by quartiles, which is the first one we're going to talk about. Quartiles, just dividing it into 4 parts. That's kind of what we're looking at. Deciles, which is 10 parts, percentiles, which is 100 parts, and we go from there. So talk about the first one here, quartiles. Yep, dividing it into 4 pieces. And I think I skipped this one here. So let me jump to this. Did we talk about the interquartile range? Yep, I see some people saying yes. Okay. Interquartile range is the Q3 minus Q1. So it's the third quartile, subtract the first quartile. You get the sort of middle ground in there. I think that's kind of where we left off. So let's do this here. I'm going to go back to our little data set over here. You guys remember this little data set from last time? Okay, and there's Q3, Q1, and Q2. Okay. This is each city or each year in the US, automobile commuters waste fuel just sitting in traffic. Could you imagine that? Sitting in traffic. Anybody lived in LA from here? No? Anybody lived kind of, sort of? Anybody lived in a very congested, traffic-y city? Okay. Where? Orange County. Okay, yeah, that's pretty close. Right? Bay Area. Okay, yeah, that was my next question, Bay Area. So the amount in gallons per year of fuel wasted by commuters in the 15 largest US urban cities in Bay Area and Orange County is going to be probably on the list there. First, second, third quartiles of the data set, find them, and then what do you observe? So real quick here, for the data, instead of having it all over the place, for the quartiles, we do have to put them in order, all in order. The Q2 is the middle, exact middle of the data set itself. Boom, exact middle here, exact middle here. Anybody else know the other name for Q2? Starts with an M. Not the mean. It's the median, right? It's the middle of the numbers if you slash from right to left. So it's the median. Cool. And then Q1 is the median between the first number and Q2. Q3 is the median between Q2 and the end. That's so cool. Okay, so now the question is this. Oh, another thing before we get started. We mentioned it last time here. Do any of these numbers look off? That's the next question. That 11 sure looks off, doesn't it? So now the question is this, is 11 something called an outlier or not? Does it fit, like, kind of fits in the data or not? Or is it something off on it? So we have a rule in statistics, and we have a computational test to see if that's a outlier or should we still include it in the data. All right, so let's go with it here. So I need you guys to first figure out for me and tell me the interquartile range, which is pretty easy. Oh, sorry, real quick here, let me go all the way here. So give me the interquartile range of the data. Should go back to the data, huh? Okay, all yours. Talk to me. I heard a 7. Everybody agreed with 7? Yeah, the formula is Q3 subtract or minus Q1. So this right here, from Q1 to Q3, why do we want this here? Is because that represents the majority of the data. That's exactly 50% of the data I already have right there. And I'm saying, look, within 7 miles per gallon, and the lowest is 23, the highest is 30. What a good data set to work with, right? Because it's almost like it's the middle of the group. Now you can actually work with it. Okay, so now the question is this: how do you figure out if that 11 is an outlier or not. What's the test? Okay, let me give you the test. So interquartile range, we just figured that one out. That was 7. Third is we're going to multiply this interquartile range by 1.5. So all yours, if you have a calculator in front of you, go. Tell me what that would be. $10.5. Okay, so here's what we're going to do. We're going to take Q3. So I got 10.5 here. That's my. So I'm going to take Q3 and I'm going to add 10.5 to Q3 to see if we have any outliers on the top end. We're good? So let's do that. So I'm going to do Q3 first. So Q3 plus 1.5 times IQR. Can you guys do that? What's Q3? 30, I think it was 30. Yep, 30 plus 10.5. That gets us. I know you know how to add. I'm just waiting for mental engagement. That's all. 40.5. Any data set that's above 40.5 that we have. Yeah, I'm going to kind of jump back and forth between the data sets here. So our cutoff was 35. Okay, sounds good. Let's go the other way now. Q1, now we're going to go down instead of up, right? So we're subtracting 1.5 IQR. All yours there. What was Q1 again? 23. Okay, 23 minus 10.5. 12.5. Okay, so here's what we got here. So if the data set was nice, the data set should land without any outliers. The data set should land from 12.5 to 40.5. And now the question is, do we have any numbers outside of that? Yeah, or else it would not be a math problem inside a statistics book. Yeah, 11, right? 11 is outside of those bounds, right? So in this case, there we go. Do we have an outlier? Yes. 11 is an outlier. Okay, we're going to get more sophisticated later on in stats about what are outliers, what are not outliers later on, but this is just the quick one. This is the one that we use for this quartile piece. Justin.
Do we always multiply the interquartile range by 1.5?
Yes, that's the number we use in statistics. And real quick here, statistics is such an interesting topic. It's not like algebra where you have these set of rules, right? You can add the same number to both sides of an equation, right? That's a rule. That's a fundamental rule. Statistics kind of changes. So what we do is we do a lot of data. We do a lot of data crunching. And so why did that 1.5 come about? Is because a lot of people agreed to it. That's why. It could have been 1.4 for all that matters, right? It could have been 2, but it's just because the data, the more we look at analyzed data, especially people that are sort of in graduate level degree that are doing research, you think about the data itself, right? Then you think about your own process, right? Like, hey, this process is not so good. I think the equivalent is almost like studying for stuff, right? There's an aspect of you're studying, like I got to study for statistics class. So you have the content of studying, and then you look back and you actually say to yourself, hey, how am I studying? Maybe I should study differently. Maybe I should study 2 hours a day. Maybe I should do this. And so it's that self-reflection part. And statisticians do that a lot. They look at data and says, you know what, that 1.5, after we looked at 100,000 data pieces, the more we think about it, maybe 1.3 would actually be a better choice, right? And then the whole statistics communities has to sort of like be on board on it, and then they change. Um, Fun fact. You guys with the fun fact? So they have, it's not like a surefire tested everything, right? But they try to do different studies about studying. You guys, it's as students, it's helpful. Okay, so the question is, what will give you the most amount of studying for the most amount of time, right? What happens? And so there's like, you just start studying and just go till you're fatigued, right? It's you got fatigue. Or do you study a little bit at a time, right? How do you do it? So seems like if you study for about 20 to 25 minutes and you take a break for 5 minutes and then you keep on going and then you study for another 20, 25 minutes, you take another break, it gives you the most longevity of studying, right? You can actually study for like 6 hours that way, right? As opposed to if you just like, I just want to study, you'll be burned out in about 1.5 to 2 hours. You're done. But so I thought that was cool. It kind of, anybody study that way? Raise your hand if you study like for about a half an hour or 20 minutes, and then you take just a quick 5-minute break. There you go, Jacob, of course. And then you, okay, how do you guys study? Talk to me. How do you guys, anybody want to clue me in on your study habits? It's all over the place, Mr. H.
I just stay in a comfortable state. Like I just sit down, like relax.
Okay, yeah, as long as you're relaxed and as long as you're not tense, then it kind of just flows and goes nice. Okay, that's so cool. No, this would be good for just as a overall kind of, do you have a time limit for yourself in any which way or no? Or just like whenever you're tired, you just kind of take a break and then you come back? Okay,
Yeah.
and
Yeah, like sometimes I take it, but it just depends.
yeah. Have you noticed the consistency of time when you do that? Like, you know, for the first hour is like 45 minutes, then you need to take a break. And then like next time is like 30 minutes, I need to take a break. Then it's like 25 minutes, I need to take a break. Or do you notice like it's really haphazard? There's no like time thing that happens.
I don't think there's that much at a time.
Okay. Not a time difference. So then about how much time before you need like, hey, I just need to take a quick break?
Usually on a Thursday, use the bathroom, stuff like that.
Okay.
Or like mine are like takes and stuff to the work, or like it's kind of muddled like with too much information.
Yeah, correct. Like when does that happen time-wise? When does that happen when your brain is like muddled? Like, yeah, I need to take a break because I'm mentally fatigued now.
I'd say it's random.
Random, okay.
But I'd say like by minimum, it'd probably be like 30 minutes. It's like,
Okay, yeah, between 30 and 45 minutes. That's cool. Yeah, that's the studies show that you get that fatigue. And so I think the study was trying to say, like, if you cut it beforehand just a little bit here, you get the extra mental capacity, but that's interesting. Cool. Anybody else want to share the studying stories? Nope. Everybody's like, I'm not telling you how I study. Okay. Okay, guys, let's go on then. Okay, we got outliers. Yes, we test for outliers. It's the multiplier 1.5. That's what we do. Let me check something out real quickly here. I want to see something. Okay. Sorry, I redid that over here on this slide because I didn't like the way it was presented here. So let me jump to what is an outlier? Outlier graphically. If you talk about graphically, there it is. There's your like, whoa. Did we do this one before? This is age of students in a statistics class.
you showed us the graph.
Gotcha. Okay. So yeah, this is clearly that's an outlier. So graphically speaking, you can kind of see, right? But then you're like, well, I'm not sure if that is. So we do have to use some kind of algebra to make that like quantitative. We're good. We can't just say like, oh yeah, heck yeah. So then the question is, okay, how about a 30-year-old? Is that an outlier? How about a 27-year-old? Would that be considered an outlier or not? You know, then it gets fuzzy. So we need to put some number context to it in that way. Okay, how do we display this quartile system? And we use it through a fun little guy, something called a box and whisker plot. fun name. Almost makes you think of a cat or something, you know, Whiskers. And I think you guys seen this before. It's very customary to see this. And raise your hand if you, or tell me if you've seen it before. Yep, okay, cool. 1, 2, 3, 4, 5. Give me the context. Where have you seen it? Say again. High school stats class. Okay, outside of a stats class, because I'm sure you guys see this as a stats class. Outside of a stats class, anyone?
Familiar, but I can't remember.
Okay. I'll see if I can pull up something here. Okay, so exploratory data tool analysis tool, that's the way we say it, but really just this. It's a good way because it highlights the important stuff of this quartile thing system. We do put a value at the minimum entry. Then we somehow delineate the Q1, we delineate Q2, Q3, and then we put a maximum on it as well. All right, and what we want to do is we want to create a 5-number summary. In fact, there's even a calculator way to do it. And it just kind of gives you that. It gives you the min, Q1, Q2, Q3, and max values. We good there? I should probably pause these, huh? So talk to me. I think everybody's done writing, or we've got two people still with it. All yours. Okay, what does it look like? Here's what it looks like. Yeah, don't write the next slide down because the next slide will actually draw it out here. So this is what it looks like right here. So you have a box and whisker. You usually have a interval underneath. We'll do an example in just a second here. And so the minimum value is this little point right here. The whiskers are on the side, and it's just a bar line coming across. And once you get to Q1, you make this little box. So, and then you got this middle line here, which is Q2. There's your median. We're good. Really quick. I like this. It's just a quick little reference, like, oh, that's where I'm at, right? So right away, you know, the middle of the group is what looks like an 18 is Q2 is 18. Most of the students, or 50% of the students, or in my mind, it's always students here, but whatever this is, the number of days people were sick or something like that, right? So anywhere from 12 to 23 or something like that, it kind of gives you, okay, that's at least the majority, the middle group, right? And then you have possibly outliers on the side, right? I don't know. If this guy went out all the way out to 40, then I'm like, whoa, yeah, that's probably an outlier. As we go from there. Okay, so let's do this for hours. So can you guys make a plot that does this here? Draw the whisker plot to represent the data. Notice we're still including the 11, right? Yeah, we know it's an outlier when we're actually going to doing like hardcore statistics. We're good. Then we're going to think about, should we include the outlier or not, right? But as far as the box and whisker plot is concerned, you want to see all the data. All right, minimum is 11, Q1 is 23, Q2 is 25. Find 30 for yourself, put a box around the Q3, Q1, and then I'll go out all the way to the max at 35, plot it, all yours, go. You know what I'm gonna do? I'm gonna start pausing the recording here. That's what I'll do so that we're not wasting footage space here. Okay, so here is the answer. So a few things. Look at your sheet of paper, look at my slide. Few things first is you have dots here, and then you got a line, a bar line that comes across here. We're good. Then you have a box around from here to 30. And then notice also, I think one person did everything else correctly, except they didn't put the bar line across here. So at the median, at the 25 marker, you do have a bar line that comes down, and that gets you that one. Okay, are we good there? All right, let you guys finish. Go ahead, finish the one. You guys finish. If you guys hadn't finished yet, go for it. No, wait just a bit here, then we'll move on here until I see everybody's done writing stuff down. All right, let's go with it here. Let's see. You do find it in Canvas. If you guys go to your, go to an assignment after our first exam, you should be able to go to grades, your grades, grade detail on it. When you hit on grade detail per assignment, right? So you overall, you have your little totals, right, that you have, right? But then you click on grade detail. When you do that, it should put a box and whisker plot for you. And then it has a little blue dot where you're at, and then it has the rest of the class, right? You've seen that before? Okay, so that's exactly what it is. The plot and whisker plot right there. It tells you the high, tells you the low, and tells you the middle. So again, what is that saying? Where's the blue dot? The blue dot is telling you your position, right, with this assignment with the class, right? So it's a position statement for you. That's kind of where things go. All right. Okay, it'd be helpful if I was showing you stuff. Ta-da. Okay. And next is, I think we've seen this before. This graph here, I want to just show you. Let's kind of go through some real life stats here real quick here, okay? And so what things say, what things don't say, right? So let's go through this. I think we've done this. Have you guys seen this one before? No, you guys haven't. Yeah? Got it. Okay, let's go through it. It was all the way in 2.1. Okay. So real quick here, a few things. So what happened was in July of 2021, in Barnstable County, Massachusetts, there was just an outbreak of COVID in the middle of summer. We good? They started, seems like the COVID restrictions were lessened so that people started meeting. And of course, it's 4th of July. Who does not meet on 4th of July, right? So everybody just kind of came out. Everybody's enjoying life. And so there's a resurgence of outbreak of COVID here. And so what happens is people come to the hospital and they get tested whether they've been vaccinated or not, or they get at least ID'd, right? If they hadn't. So what happens is this guy here, the light blue on top is people that have been fully vaccinated. The dark blue is the numbers that are, and this is the month of July. So it looks like July 6th is the first case. And then we kind of go from there. There's an uptick, and then eventually there's a downtick afterwards here. So the middle of the road is right here, which is what, 14 days after 4th of July? About there, right? The middle ground. So it seems like, yeah, if you're going to show signs, maybe something after 4th of July, right? Because it usually takes about maybe 10 days to show, or less than that to show symptoms. Anyways, you guys talk to me here. You guys talk to me, what is this data telling you and what is it not telling you? That's kind of the question here. If what? Yeah, how much did, how much didn't, and the number of people that are here. I didn't give you the crunching the numbers here, but it looks like 74, I think it's 74% of the people here are vaccinated and they got COVID. Here, and only 26% of people that are unvaccinated are here, right? So in the study. So it's not actually, it's an observational study, right? It's not an experiment, right? We didn't experiment on it. It's just the numbers that are coming us naturally. Okay, anybody talk to me? Any thoughts, anything that kind of comes across here? So I'm gonna throw out some stuff at you in just a little bit here. So it seems like on the onset, if you just look at the data, right? It seems like, hey, if you get vaccinated, you're like 3 times more likely to get the COVID or not, right? But then the question is that true? So these are people that have come to the hospital, right? Because of COVID symptoms. And this is the report. So anybody, any thoughts here? We can discuss the thoughts.
The type of
Say again, Zero.
the type of gatherings, like, were they like, what's the ratio between the vaccinated and the non-vaccinated when they were together during the gathering?
Oh, gotcha. Okay, so yes, so it could be that the vaccinated people, because they were more confident, like I got the vaccine, right? They actually went to the gatherings, and it could be that the unvaccinated people like, we're not going to go, right? So you don't know the percentage of the gatherings to compare to this, right? Because if 74% were vaccinated, 26 were not, and then we get this same number, that means it's a 50-50 correlation, right? Instead of a 74. Absolutely. How about this? Vaccinated people, would they be more likely to go to hospital if they're sick? Or unvaccinated people? What's the likeliness of people going to the hospital? Sorry, could you just say a little louder?
If you have the vaccination, you're not going to the hospital.
Okay, got it. That's cool, because I was thinking the exact opposite here. So Quincy says, look, if you're vaccinated, you're thinking like, hey, I'm vaccinated, I'm okay. Maybe it's just a cold because I'm immune to COVID, right? I was thinking the exact opposite. I'm thinking unvaccinated people, because there's almost like already a mistrust of the medical establishment. That's why they're unvaccinated. So it could be that they don't go to the hospital because they don't trust the system in the first place. So it could be the unvaccinated people are actually underreported here. And Quincy's actually arguing the exact opposite. It could be that vaccinated people are underreported here. The stats could be even higher. Okay, guys, did you guys see the difficulty of statistics? That's what I want to point out to you, right? It's not just like, oh, here, this proves something. Like, no, let's talk about what are the strengths and weaknesses of this thing, right? And that's why we do need 2, 3, 4, 5, 6 different studies and all of that sort of coming together like, hey, now this is painting a picture for us, right? That's kind of what we're looking at. Okay, why did I bring this up? You don't know, because I haven't told you yet. So on the next one is this little chart right here, which is kind of interesting, is the same study. And so it seems like, so notice the N number here, N number is 84, and the number here is 127. So originally, let's just jump to the details again. Originally, the number was 469, is that right? You guys see the 469 or no? Okay, just want to see if you see it from the back. There's almost 500 people here. In this study, there are what, 200-ish, right? 200 people. So I'm not sure if these people is it a good sample from the 500, right? Now we're doing a sample from the sample, right? Or the population that came in. And so, but what is this? What is this telling you? This is how much it would call a viral load you have on your body, right? How much of the virus is impacting your body. And so I can't, I don't know if the CT value, the higher it is, the better, or lower. I don't know. I forgot which way it goes. Okay. So we won't discuss that for an instant. But what do we see? This is a box and whisker plot. It's a vertical box and whisker plot. We good? First things first, you don't see dots in here. We see actually just dashed lines. And the more I've looked at box and whisker plots in general, like not in a textbook, I see it more like this right here. It's actually more like a vertical thing instead of horizontal. I don't know, 60-40 maybe, 60% of the time you see it vertically, 40% of the time you see it horizontally. Anyways, so this kind of tells you another one. So they took a sample, looks like, of these guys. And the viral load, what do you guys say? Is it different or is it the same? You guys talk, what's the consensus of the class? Different or the same? Okay, let's show of hands here. How many say, you know what? The data looks like it's kind of like it's similar. It's pretty similar. 1, 2, 3. Okay. Hands down. How many say, Mr. Rajiv, the data looks very different. It's very different from the other one. Not very, or it's different. Yeah. Well, why do you guys say it's different? Go ahead. Talk to me. Why do you say different?
Yeah, like the box, it's more packed, and the maximum is higher compared to the other boxes.
Okay, yeah. And that's cool. You guys say that guys that said actually it was the same. You got to defend your argument. Go. Why is it the same? Oh, no argument. You just raise your hand for the fun of it.
Because the median is kind of the same.
Yeah, median is like 22 versus 23. Like that is like one CT value off. Like I don't think that's going to be big, especially when the CT values go all the way to 40. You're talking about the median being 22, now 23. Like that looks the same. Jocelyn, good job for recovering for those guys. Oh, same thing. Yeah, now you're going to ditto it. Yeah. Uh-huh. Yeah, so here's what we're going to do in chapter 6 and 7, where we have something called two sample statistics. I think it's chapter 7. Two sample statistics says this is this sample, this is this sample. Are they the same or different, right? And we're going to have to put some numbers to it. Once that number comes out, 4.2, we're going to say, yes, that's different, right? 8.7, like, dude, they're the same, right? So we're going to have to do that. And again, we've just put numbers to things. That's all. Okay. Hey guys, real quick, does that kind of at least kind of give you the difficulty of stats a little bit here, right? It's not just one picture, you got it, you're good. It's not algebra where it's like you add 2 to both sides, divide by 3, and you're done, right? It's a different little process here. Okay, guys, with that said, let's jam to, and it should not be. It's not like you fall on one side like, that's it, think through things. That's part of it. You have a critical eye towards things with numbers. Okay, next one is we're going to talk about is percentages or percentiles. And I think, let's see if we finish up on that here. Nope, got a little more to go. Percentiles, and we're going to go quickly of this here. I'm going to give you an example in just a second here. Let me give you some formulas here. So SAT scores, that's a perfect example. This person here, which got it's like a 1250. A 1250, they would be in the 80th percentile right there, 80th percentile of the data, which means they scored better than 80% of their peers. We're good in it. So what's the formula for it? Formula for it is right here. This one you probably want to write down at least. Just put percentile on top and just put percentile of X is the number of data entries less than X divided by the total number of data entries, and then you multiply by 100. And that should be highlighted here. So not sure why it's not. Same thing, I'm highlighting this right here, right there, and then all this right here. Yeah, I think I like lecturing from here a little better. Got all my tools here. Okay. All right, then what we do is we actually round to the nearest whole number. So you will never get a percentile rank of 99.7 or 24.6. You're going to get the 82nd percentile, the 31st percentile. So let's do an example with this one right quick. All right, good to go. Guess we'll do this. Dun, 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 dun. Dun. Okay, we're good to go? Good to go? So you got to count. So this is a counting process, right? Counting of the number of entries that are less than the X value that you want. We just count how many total entries you have there, multiply by 100, and you're good to go. All right, so I have this in order. Are we good to go? Got it. Okay. Got a few people still writing, but I'm not sure if you're writing that here. So I have this right here. Percentile. Find the data set in the second example. Find the percentile that corresponds to $34,000. So this is tuition costs in thousands of dollars for a specific college. And so we're trying to get to 34,000. So all yours, guys. Talk to me. Let's see. How many data entries are there before you hit 34,000? And don't need to write down the data again. That's not what we want to do. We want to just be able to compute it. I heard 8. Is that right? 8. Everybody agreed with 8? 8. 8 data entries. 1, 2, 3, 4, 5, 6, 7, 8, and then you hit the 34,000. That's cool. How many data entries total? 34. No, not 34. 34 is just a number. I don't think that's. Oh yeah, 34,000 corresponds to the data entry of just 34 because it's in terms of thousands. 25. I heard 25. Everybody agreed with 25? Let's jam. Let's go with it. 8 divided by 25 on your calculator. Multiply by 100. Let's see where we're at. What percentile rank would that be? $36. I heard 30. 32nd. Okay, got it. Yeah. So we'll get an answer of 32. What does that mean? That means that $34,000 corresponds to the 32nd percentile. We're good. There it is. 32nd percentile ranking. So for $30,000, what does it mean? The tuition cost of $34,000 is greater than 32% of other tuition costs. That's what we're talking about. Right? It's you compared to the others, or this compared to the others. Something called one more thing to cover, the standard Z, it's called the Z-score. The standard score is something called the Z-score. think we do that real quick here. Boom, 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 and then we'll go. So it represents the number of the standard deviation thing keeps on coming up. Standard deviations given X falls away from the mean. So this is X. The mean or the mu value was that. Question is, how many standard deviations away is that X value? Okay, formula. Got to give you the formula. There it is. Z is our variable now. It's the value of X minus the mean divided by standard deviations. Cool. Say it, say it. Uh-huh. All right, we're good. Let's show you just some practice items and then we'll actually do it ourselves here. So first things first, let's do this one right here. So the mean speed of vehicles along a certain stretch of highway is 56 miles per hour. That is not California, that's for sure. Standard deviation is 4 miles. So every 4 miles, you're 1 standard deviation away, right? So you measure the speed of cars traveling. One is traveling 62 miles an hour, one is doing 47, another one's doing 56. So just for you guys to sort of see the z-score in action real quick here. Find the z-score of each one. The one thing is, here it is. We have to assume that the distribution is that normal curve that we talked about, right? It goes up and then comes back down. That's the assumption. All right. Not going to make you guys compute it. Just kind of look with me here. So if that is the case, 62 minus 56 divided by 4, that gets you 1.5 standard deviations away. And notice it's positive, right? Because 62 is bigger than 56. Z-scores can also be negative. If you're traveling 47 miles an hour, minus 56 divided by 4, now you're at a negative 2.25 or 2.25. Z-scores could be negative. And if you're traveling exactly what the mean is, then you're going to have a z-score of 0, which means you have not deviated from the middle at all, right? You're right at that middle. That's what you're looking at. Okay, now the calculation for you guys. Here it is. I have the mean heights and standard deviations for the population of men and women. And I think this is internationally. It doesn't say the US, so I assume it's international. So let's see, internationally, here it is. Men's height is 69.9 inches, which is just shy of 6 feet. Is that right? No, that's 70 inches, right? I assume 72 is 6 feet, right?
Yeah.
Yeah, so a little under 6 feet tall, right? 5 what? What do you guys say? Like a 5'9" ish, yeah, about there. All right, and the standard deviation is 3. Interesting. For women, about 4 inches, 5 inches lower than that. And the standard deviation is actually a tiny bit smaller. So there's actually a little bit less variation for women than men, just slightly. Okay, here it is, guys. Can you give me the z-score of a 6 foot tall male and a 6 foot tall female? And then we'll talk about it. We're good? That's what I need. I need compute the z-score for a 6 foot tall male, then a 6 foot tall female. All right, give you guys a little bit of time. Okay, just so you make sure that we understand this here. So we're going to compare z-scores. So that's fine. Oh, that's why. Pin. All right, guys. For a 6 foot tall person, 6 feet tall, 6 feet times 12 for inches, that gives us 72 inches, right? So X is going to be 72 inches for both the male and the female. That's what we're trying to figure out. We're good? So X is 72 for the men. Mu is this standard deviation. Okay. I think I went around the room. Everything's good to go. I think everybody got the same answer here. Here's what I got here. So the 6 foot tall man, what we did is we did this. We did 72 minus 69.9. That answer itself get divided by 3 and 0.7 is what we got, right? Cool. For the 6 foot tall woman, there it is. There's the value. So kind of careful. Notice you're dividing by 2.6 now, right? Because that's the standard deviation for the women. 2.6. And I see some people doing erase marks. So talk to me if you need to, or tell me what went wrong. And this one, it says approximately. I didn't like that answer. Approximately. No. I don't think so. No, it's going to be 0.7. Was it exactly 0.7? Okay, got it. I would go like this. I would say this is about 2.96. I would rather have that. 2 decimal place accuracy for z-score. That's normally. Okay, so what in the world are we talking about? Here it is. And we'll finish up with this slide here. And here's, if you want to draw something out on your sheet of paper, maybe this would be the best one right here. It is inside your textbook, I believe, as well. So what do we talk about? Talk about z-scores is super duper important. We say things are normal or usual and not usual based upon the z-score. And it has been the most used type of statistic. So what's up with that? Anything that is less than 2 standard deviations away, we call that usual scores. Everything is fine. So for a man to be 6 foot tall, usual or unusual? That's usual. Any z-score that is between -2 and +3, between a 2 and 3, or going the other way, between -2 and -3, it becomes starting to become unusual. That's not something that we normally would find. Now, if you are now past 3 standard deviations away, this is now highly unusual. So, and these things are not like clear cut. So I'll let you guys write that down first. I want to explain to you what. Cool, that graphic is really important to know. We're gonna use this quite a bit. And so next thing is we gotta understand, this is not algebra. This is not like everything is clear cut. Not the answer is like, this is 2.96. It doesn't function that way in statistics. So the question is, look, we got 0.7. 0.7 is like right inside here. 6 foot tall man. Yeah, that is typical, right? The women was 2.96. We don't say like, well, it's 2.96. It's not really 3, it's just 2.96. We don't argue those kind of things. Like, is 2.96, is that pretty close to 3? Yeah, so a 6 foot tall woman is pretty like unusual. Yeah, all like very unusual. Like it's on the border there, right? So that's kind of it's what do we say, till a little bit fuzzy numbers, yes, but then there's still consistency, right? There's still consistency. Yeah, so 2.96, hard number, 2.96, yes, but come on, it's 3-ish at that point. It's borderline over there. Okay, guys, we stop here for the day, or we stop here because we finished up 2.5.